All right, so you should see that now. Good. All right. Hi, everybody. Welcome to the second bit of this tutorial. As I said, it is Explainability in Machine Learning, a basic introduction for the uninitiated. And the idea here is to really give you a bird's eye view of what's happening in the explainability landscape in machine learning. Okay. Let's now, given that we have provided all this context on explainability, interpretability in particular, let's kind of think about where does it all fit? How do I go about it? Which technique should I use, et cetera, et cetera. Obviously, there is no, clear and unambiguous answer to these questions, and it very much depends on the application at hand. But nonetheless, I think there are ways in which you can look at the range of techniques that have come up in the area and try to place them, at least mentally, where they might fit in and what they might be useful for, okay? And let's try and do this in this slide deck. What I'll do is I'll think about, I'll try and create a narrative here about a data scientist working for a company called Jane. And what she's trying to do is she's looking at credit decisioning. Okay, so she's looking at an application and deciding, for instance, should we grant this person some kind of loan or mortgage or whatever. And obviously, this decision is based on a number of features, like, for instance, the person's salary, the person's age, the person's family status, where they live, credit history, et cetera, et cetera. So it's based on a number of features. We won't care about the exact nature. So this is just an abstract example to kind of motivate what we will be discussing in the slide deck. And thinking back about what we mentioned, right, in the previous slide deck, even though we understand that explainability and accuracy are not really at odds at each other, we will still kind of play with that scenario and think, okay, there are many possible models she could go for, and what she wants to improve is to achieve maximal accuracy, but also have a lot of interpretability or explainability with her approach, okay? So, this is an informal picture, and this is roughly what she's trying to do. And so, obviously, the questions that's going through her mind is, what model should I pick? How do I enhance explainability? What can I do to improve the transparency of the overall procedure to my manager, let's say, or some kind of stakeholder, okay? So it's a very high-level picture that we're trying to draw here. And really what we can say is that there is a trade-off between what kind of model she chooses and what kind of techniques to go for, okay? So she can go for a transparent model, which seems like the obvious choice, or she can go for an opaque model. And the difference here, thinking back about what we discussed in the previous slide deck, is that transparent models are often easier to read. A good example is something like logistic regression, where the final decision is based on a weighted sum of features, okay? So it's saying the most weighted feature might be income, the second most weighted feature might be age, right? So this is kind of telling you what kind of features influence the final outcome. And this is obviously a bit easier to read. So in this informal sense, it has high explainability. We can contrast this to an opaque model like a random forest. If you aren't familiar with the random forest, it's like a decision tree, except that it is based on a random sampling of the data. So many such trees can be constructed. And the nodes in these trees are, again, like a decision tree based on certain choice points. So for instance, is it raining? Do I carry an umbrella? Do I not carry an umbrella? If there's red in the image, then I should call it a fire engine. Otherwise, I should call it something else, et cetera, right? And you have a whole range of these. And basically, you rely on majority voting to decide what the outcome should be. So each tree will give you some decision for an input data point. You go across all of these, and then you collect the majority, and you decide what to do. Now, you don't really understand so many trees, right? If you think about, 6 or 7 trees, or even 100, and then go up to 100 trees, you really, there's no easy way to understand the overall logic of the system. So it has a complex interpretation. but we could kind of say perhaps it is offering very high performance. Okay. Just to provide some clarity to this picture, there are the most common type of transparent models you might think about are things like regression. You can use k nearest neighbors, where you cluster data points, and then the decision is based on which cluster the data point falls to. Obviously, in the 80s and the 90s, it was very popular to use rule-based learners, right? They're learners that produce rules, and these rules are easy to interpret. Decision tree is the example we have been often referring to throughout this tutorial, and Bayesian network is another very popular transparent model where you can understand the cause and effect structure for your overall decision. Okay, so these are common transparent models. And some common opaque models are things like these: random forest, support vector machine, or a neural network. Needless to say, I'm not really going to describe any of these, right? As I said, I will keep this tutorial at a fairly high level. As far as you have some kind of familiarity with what these are, it's fine. And if you don't, feel free to just speak up and I can give you a quick explanation of what they do. Okay, but it doesn't really matter. You won't see any of these again. It's just to provide the stage and what the key players are. Okay, let's imagine this scenario where she tries one of these transparent models. Let's say she tries a regression model. It doesn't work so well, and she decides to use a random forest. Okay. And now we are in the situation where she has used a random forest, but of course she has to find a way to explain what the random forest is doing to her manager or whatever. So what should she do? Okay. The first thing I think, and this is very common in many industries right now, certainly banks, is to try and use a technique called SHAP. And for those of you who work in game theory, it's actually useful to read this up because SHAP has game theoretical foundations, and it really is based on the idea of a payoff. So if you think about a number of players in a game, what is the expected contribution for each player is what you're trying to compute. And when you apply this to a machine learning setting, this is a bit like saying, what is the expected contribution for each of the different features? So in a way, the SHAP value that you get for each feature tells you how important that feature turns out to be. So, if you think about the application we have in mind, which is whether to approve loans or not, things like your annual pay, your age, your marital status, the kind of assets you have, etc., are all going to be important factors in explaining. Okay, so it provides a good perspective, I think, in trying to tell you what the most important features are. Now, you should note the similarity in this sense with something like a logistic regression, right? Because as I told you, in logistic regression as well, what you get is a weighted sum of features, but we have dropped logistic regression, we have used random forest, but nonetheless, using Shapley values, we kind of get a logistic regression type analysis of what the model is doing, right? It's kind of telling you which features matter the most and how important are they compared to other features, right? So this is quite a good model to get an understanding of how the decision works. All that's good, but let's assume the manager comes back and says, I like this analysis. I like that you were able to tell me which features matter. But let me ask you this question. What can we expect because of COVID and the economic downturn we're seeing nowadays? What can we expect to happen when salaries of customers start to decline, right? Now, how would Jane do this based on the plot, right? And if you think about it, there isn't an obvious way to do it. You could try to look deeper into the plot and try to play with different values for a certain feature, such as salary, and try to navigate this plot and come up with some kind of explanation. But it's not easy to do, right? Certainly not obvious, and in a way not convincing enough potentially for the stakeholder to truly understand what the model is doing. So SHAP is great, right? But it's not, feature importance models are not really going all the way to answer such types of questions. I won't discuss this in this tutorial, but it turns out that there are other issues with SHAP, okay? So depending on the type of SHAP you use, there are some problems that come up, including that they can be easily fooled using adversarial attacks, okay? I won't go into this, but you can look this up if you're interested in SHAP. So there are problems with SHAP. So what does Jane do? I mean, to analyze how exactly the salary is an influencing factor on the overall outcome, she can consider these plots called ICE plots and partial dependence plot. What this looks at, if you look at the left-hand side, what this is basically telling you is the probability of approval based on for certain values of income. So you're looking at income on the x-axis, and you're looking at income going from say 20,000 all the way to 80 and 100,000, and you're kind of looking what's the probability of approval for this. Now, one thing you'll notice when you look at this plot, even though this plot is not based on accurate, real data, what you can expect to see in such plots is that there is a sharp peak between say 50 and 55,000. And then it starts to drop, right? It starts to drop after 60,000. And you might wonder, well, why should it drop? Why shouldn't we expect to see a steady rise? And the reason for this is that there can be other features that come into play when the income goes beyond 60,000. So for example, perhaps it is the case that in the country where the study was done, a salary of 60,000 typically is an employee who's been working for a few years. If that's the case, perhaps we can expect this employee to have children and be married and own a house and own some mortgage. So all of these factors might be influencing the possibility that this person can pay back, right? So obviously the limitation of a two-dimensional plot is that you cannot really inspect some of these other aspects that are obviously contributing to the probability of approval just because the income goes up. So there are these other aspects that are limited. So you can go to a three-dimensional plot, but that's it, right? So at some point you have to consider auxiliary ways of explaining the interaction between these different features, right? The ICE plot is kind of based on the same principle, except that the ICE plot gives you a per instance plot. Okay, so for every data point, it plots this thing. It plots the probability of approval. And what you can see again is a cluster of points. So basically, you're saying a majority of my customers are really those who are, falling in certain income brackets. And it turns out my approval is so and so for those customers. Okay, so it gives you this level of detail in terms of controlling what for one specific feature such as income, and gives you an insight on that. So in a way, going back to the stakeholders question, Jane is able to provide some insight on this. But then the stakeholder goes on and says, what can we say about a specific individual? Can you provide some more discussion on that? And so what Jane decides to do is that she decides to consider a technique called counterfactuals, okay? And what counterfactual does is that it tries to look at a perturbation of the original data point with respect to one or more features. So for instance, she sees that if you consider the same individual, but you consider the case where the income drops by 50%, then you would reject this application. But if it was only decreased by 25%, you would still approve it, right? So you can play with these change of features. So in a way, counterfactual explanations tell you about what changes need to be made for the decision to be flipped. And this is quite interesting for the stakeholder, obviously, to get a sense of what's happening with these data points. Likewise, Jane could also provide rules that characterize X and all the data points in the vicinity of X. She can say things like, well, if the income is greater than 20,000 an annum, then the status is to accept this person, otherwise you reject it, right? So you can provide local rules for this. Now, you can also flip this aspect, and you can also think about debugging the model using explainability techniques. For instance, if the stakeholder comes back and says, I'm a bit worried about the data point for Mr. X. Can you tell me how the model would behave if X was removed? And Jane can then replot the model and using a technique called deletion diagnostics and tell you what is influencing the decision boundary the most, and she can explain that in fact X is not a critical factor in the way the model behaves now. More generally, she can use global rules, right? So these are the other explanations were local, but she can also resort to global explanations and extract rules of the model as a whole to tell you how the model behaves. Okay, so this is a case where she uses a certain technique called entries, which is a model specific, so it's mainly for random forest, but it's global, okay? And so it has a lot more power. If you remember from the first slide deck, that global explanations are much more attractive because they give you a perspective on the whole model, okay? So to put things in perspective, SHAP or feature relevance is an interesting approach as a first step in trying to understand how features influence the decision. But as soon as you want to play with other aspects, like looking at the model's change as incomes rise or fall, or looking at an individual and looking for ways in which the application could get rejected, or looking at the decision boundary, different techniques come into play. Okay, and here I've only looked at 6 techniques. You can go through, the area identifies a whole range of other techniques that all, in some sense, all provide some perspective on how the decision boundary works and how it might, in a way, improve or at least inform you of how to change the model based on the kind of question you're looking for, right? So ultimately, the kind of questions you're interested in could influence which technique you want to consider and what these techniques do, okay? So let's reflect for a few minutes what we have right now in terms of the concepts we've covered. And I've left a few questions for you to reflect on, but these questions are should be self-explanatory. So I'll just let you look at them for a few minutes. Feel free to ask me questions if something is not clear. But in a way, we've answered these questions, right? Specifically, if you're looking at the last one, as I identified, all the other techniques were local except for entries, which was a model-specific technique. And moreover, it was global, right? So that differentiated that particular technique from the other ones. All right. So what exactly is the difference between model agnostic and model specific? As we mentioned in the very first slide deck, the first is one that applies to any ML model, whereas the other one is looking at the architecture and trying to do something clever. So obviously, in terms of the explainability type, if you look at the second last row, model agnostic techniques typically exploit the inputs, outputs, and do approximations, whereas model specific techniques can be customized and simpler and deeper, okay? It turns out anyway that model agnostic techniques also are somewhat more popular because they can be applied to a range of different models and different architectures, and model specific techniques turn out to have fewer libraries and so on, okay? In some sense, using a combination of these two is a good thing when you're trying to convince a stakeholder about what the model is doing. All of this leads, I think, to a kind of pipeline. How would you go about enabling or talking about explainability? Obviously, the most simplest thing you want to do is consider a transparent model, right? If your data is small and a transparent model itself turns out to be small, then you're good if you're achieving high accuracy because you have a really nice way of understanding what the model is doing and it's transparent. But if it turns out that the transparent model as well is very large, you might as well go for an opaque model. But regardless of which model you go for, exploring post-hoc explainability is a very healthy option to consider to inspect how the model works, what its salient features are, what are the brittle points, looking at robustness, etc. Post-hoc explainability helps a lot, okay? And again, what you should be looking for in explanations, you're trying to debug the model, understand what the model is doing, improve trust, right? Understand the limitations of these models and so on. So in a way, it is really like code debugging, except that it is done at a much higher level. And you need to play around with a series of techniques to poke at the model from different sides and get some analysis and understanding of what the model is doing. What I will do in this last bit of the slide deck is that I will tell you some ways we can potentially think about the number of different techniques coming up in the literature, okay? And I'll position them in terms of so-called frameworks, okay? I'm calling them frameworks simply to say there's some kind of table or figure or whatever that tries to taxonomize and organize the different techniques out there. You can call them whatever you want. They could simply be called a table as well. And the purpose really is where do I go to identify which technique I should be using and how many of them should I use, which ones are appropriate for the application at hand, etc. And for all of this, you need a way to structure and navigate the landscape. And so the frameworks that I've put in here are, I suppose, a decent starting point, okay? Let's look at the various options that we have. These are also drawn from the literature, I should add, so they're not all from us. There are some references at the very end that tell you which literature we drew from to draw up these frameworks, okay? The first thing you can do is you can think of them as a kind of taxonomy, right? So, and this is basically covering everything that I've discussed so far. That is, we have certain types of models. We have transparent models or we have opaque models. One way or another, we can enable post-hoc explainability. And there we can look at model agnostic versus model specific. And each of those can be furthered by different categories, such as simplification or local explanation. And then you have certain principles that are driving these techniques, right? So an example here is if you look at SHAP, which we talked about, as I mentioned, is inspired by game theory, right? I suppose the explainability principles themselves don't necessarily matter that much, at least in the initial stages. But clearly, if you want to develop, let's say, a new version of SHAP that has interactivity built into it, then you might want to, consider other techniques that are based on interaction and see if you can create a hybrid model based on these different approaches, right? So that's the kind of insight such a taxonomy could provide. Okay. Just stop very quickly in terms of reflecting on what we have right now. And again, the questions are kind of obvious, but just to reflect that we looked at the cheat sheet and the taxonomy framework. Okay, let's look at other frameworks besides the taxonomy framework that could be useful here. One thing that's useful to think about is in terms of transparency. I'll just focus on the second row here, decision trees, and to reflect, we are able to simulate it, right? Because these are trees, we navigate the trees. They are understandable in the sense that you can look at a subtree, so they're decomposable. And we also understand the algorithm because we are navigating and traversing the tree. So in some sense, post-hoc is not needed, provided these decision trees are smallish, right? As soon as they become large, we then have to think about post-hoc explainability, okay? I won't go through the other ones. There are some references on where you could look these up if you're interested, but this is another way, right? So if you have a model that offers things like the ability to simulate it and decomposability and transparency, then they might be attractive, provided they are smallish when you consider the application at hand. Obviously, if you have a lot of data and you end up using an opaque model, then you want to think about post-hoc explainability. The other way you can think about different advances in the literature is just categorize them based on what assumptions they make and how broad they are, right? So for instance, can they only work with discrete features? Can they work with continuous features or both? Do they make certain assumptions about independence between the features? Now, this is actually a very critical and dangerous assumption, right? Certain approaches make the assumption that features are independent of each other. So it's a bit like saying the gender of the person and the school the person they went to, this person went to is independent, although it may not even be true in principle. And so this independence assumption does matter, and it can mean that you have an incorrect understanding of the model if you make this assumption, okay? So yeah, so this is, again, as I said, there are references towards the end where you can look up different techniques, but this is another way of thinking about, what are the assumptions behind some of these techniques? Do these assumptions matter to me, and do they matter in the application, right? Finally, it's also worth putting in mind what kind of advantages and disadvantages the different techniques offer, right? So for instance, looking at the second row again, examples is an attractive way for an explanation because they give you representative data points, but the disadvantage is that it is up to you to figure out what really distinguishes or is important in these examples that categorizes them as a representative example, right? So if you have an example with 20 or 40 features, you need to figure out which of those features is really what's making this a representative example, which is kind of challenging, right? So what's really happening in the literature, I think, are people are trying to combine some of these different categories and trying to offer you the best of all worlds, right? So that's pretty much where research in explainability is looking like. So if a lot of recent literature, for instance, tries to look at interactivity as a mechanism to get better explanations, where they might then offer a plethora of different categories based on what the user's input is, right? So yeah, so you have combinations of these different techniques based on what you're looking for, okay? Let's look at this first question just to refresh our memory. If you wanted to find an influential instance, what type of explanation should you aim for in the explanation type? And if you look at this and think about it, it's clear that it should potentially be the example type, right? Because an influential instance is an instance that's telling you what the model's decision boundary looks like. So clearly, looking at examples, prototypical examples, will help you identify what are the examples that are ultimately deciding how the model behaves. So influential instances are essentially example-based explanations, okay? As it turns out, we will delve a bit deeper into influential instances shortly. So that's the key takeaways. Let's think about some framework questions for now, some open questions. The first one is relatively easy to answer, right? As we said, if you have decision trees with many nodes, then it is obvious that it's hard for the human to understand what the model is doing. So in this case, post hoc methods can help. And the second question, whether local explanations can also be visual explanations, the answer is potentially yes, right? Because a local explanation is simply looking at a local region or a data point, and there's no reason that it shouldn't also be a visual one, right? So that's where we are in terms of the framework. And this is a very short bibliography from which this material was drawn. I will, as I said, since I'll include a recording of this, you can look this up, and I can also include the details on the web page. So this is the second bit on the tutorial. I'll stop the sharing and the video for now, and we will come back in